Imagine enduring a grueling 7-hour ferry ride from Shenzhen to Zhongshan, only to now zip across in just 20 minutes, thanks to a breathtaking 15-mile sea-crossing bridge. China, the world's most populous nation, is rewriting the history of infrastructure with over 1 million modern bridges. Towering steel spans stretching dozens of miles across oceans, soaring suspension cables reaching thousands of feet above canyons, and unyielding concrete pillars, taming raging rivers, stand as testaments to this nation's engineering prowess. Each bridge is a marvel shattering records for length, height, and sheer audacity. Join Top 10 Discoveries Official as we unveil the top 20 largest bridges in China, masterpieces that leave the world in awe. Picture a province like Guizhou, often hailed as the Museum of Bridges. Over half of the world's 100 tallest bridges stand here, each a feat of engineering brilliance, conquering canyons thousands of feet deep and sprawling rivers. What fuels China's remarkable achievements? It's a potent blend of ambition, vast resources, and cutting-edge technology. China pours 8–10% of its GDP into infrastructure equivalent to hundreds of billions of USD annually, compared to just 2–3% in the United States. The result, over 10,000 new bridges built each year, ranging from modest rural crossings to record-shattering global marvels. The hallmark of China's bridge projects is technology. The Beidou satellite navigation system, boasting pinpoint accuracy surpassing GPS, enables engineers to align every inch of bridges spanning dozens of miles. Artificial intelligence AI monitors projects in real time, ensuring safety and optimizing materials, while automated robots accelerate construction timelines. These innovations not only allowed China to smash records for length, height, and main span, but also set bold new benchmarks for the global construction industry. In contrast to the US, where infrastructure projects often drag on for decades, China completes colossal bridges in just 5 to 10 years. From the world's longest bridge stretching over 100 miles to suspension bridges soaring beyond 2,000 feet, China is redefining the art of engineering. These bridges are more than transportation links. They are powerful symbols of a nation rising to global leadership, inspiring awe worldwide. Coming up next are the 20 largest bridge projects in China, where Chinese engineers turn the impossible into reality. The Danyong Kunshan Grand Bridge, stretching an astonishing 102 miles, holds the title of the world's longest bridge, serving as the vital artery of the Beijing-Shanghai high-speed railway, a feat that leaves the global engineering community in awe. Compared to the Lake Pontchartrain Causeway in the US, which spans a mere 24 miles, this bridge is over 4 times longer, showcasing the unparalleled ambition and project management prowess of Chinese engineers. Completed in 2010 after just 4 years of construction at a cost of $8.5 billion, this monumental structure is not just a transportation link, but a bold symbol of China's dominance in global infrastructure, dwarfing U.S. railway bridges like New York's Hellgate Bridge, which measures less than a mile. The project consumed 450,000 tons of steel, enough to construct 65 Eiffel Towers, and 3.3 million cubic yards of concrete, with over 2,000 piers spanning rivers, lakes, floodplains, and farmland. A standout engineering innovation is the advanced modular assembly method, where 100-foot bridge segments were prefabricated in factories with precision under 0.2 inches, then transported and assembled like colossal puzzle pieces. This approach slashed construction time by 30% compared to traditional methods, saving hundreds of millions of dollars. To ensure stability on weak terrain, engineers employed precast pile technology, with each pier cast on-site, using high-strength concrete to withstand the immense pressure of high-speed trains traveling at 217 miles per hour. Chinese engineers also utilized 3D seismic simulation technology to analyze earthquake impacts across the bridge's 100-mile span, ensuring safety in a high-risk seismic zone. High-capacity hydraulic cable systems were deployed to transport bridge segments weighing hundreds of tons across complex terrain, a technique never applied at this scale in U.S. projects like the Hellgate Bridge. With over 10,000 workers coordinating seamlessly, the project was completed 2 years ahead of schedule, a remarkable achievement that U.S. infrastructure projects struggle to match. The Danyong Kunshan Grand Bridge has slashed travel time between Beijing and Shanghai from 10 hours to just 4, transporting over 100 million passengers annually and boosting cargo traffic by 20%. This has contributed over $50 billion to the region's GDP through enhanced trade and tourism. The project generated more than 80,000 jobs during construction, from engineers to transport workers. Socially, the bridge has improved access to education and healthcare, with a 15% increase in students from nearby provinces attending universities in Shanghai. Unlike the Hellgate Bridge, which primarily serves urban transit, the Danyang Kunshan Grand Bridge has a national economic impact, solidifying China's position as a global transportation hub. The Hong Kong-Zhuhai-Macao Bridge, spanning an impressive 34 miles, stands as the world's longest sea-crossing bridge, linking 3 major economic hubs of the Greater Bay Area. Compared to Florida's 7-mile bridge, which stretches a mere 7 miles, this engineering marvel is nearly 5 times longer, showcasing China's unmatched expertise in conquering harsh marine environments. Completed in 2018 after 9 years of construction at a cost of $20 billion, this bridge is not only a transportation triumph, but also a powerful symbol of economic ambition, positioning the Greater Bay Area to rival Silicon Valley. The bridge system comprises a main bridge, a 4.2-mile undersea tunnel, and 4 artificial islands utilizing 420,000 tons of steel and 2.5 million cubic yards of corrosion-resistant concrete designed to withstand Category 16 typhoons with wind speeds of 125 miles per hour. A standout innovation is the rapid artificial island construction technique, where engineers deployed massive 6,000-ton concrete blocks installed at depths of 130 feet using underwater cable systems. Each island was completed in just 6 months, a pace unmatched by U.S. marine infrastructure projects. The undersea tunnel was constructed using 590-foot-long steel tubes sealed with high-powered plasma welding technology to ensure zero leaks in high-pressure conditions. To ensure safety, Chinese engineers employed 4D wave simulation technology, analyzing over 5,000 weather scenarios to design a bridge capable of withstanding 20-foot waves. Bridge segments were assembled using automated welding robots, reducing errors to under 0.1 inches and boosting construction efficiency by 25%. In contrast, the 7-mile bridge, built with 1980s technology and taking over 7 years, pales in comparison to the speed and complexity of this project. The bridge also integrates solar-powered lighting, supplying 30% of its operational energy, a sustainable innovation yet to be adopted by U.S. sea-crossing bridges. The bridge has slashed travel time between Hong Kong and Zhuhai from 3 hours to just 30 minutes, increasing cargo and passenger traffic by 35% and contributing over $10 billion annually to the regional economy. The project created more than 60,000 jobs, spanning construction, tourism, and logistics. Socially, it has fostered cultural exchange with a 20% surge in tourism between Hong Kong and Macau, while improving access to healthcare and education services. Unlike the 7-mile bridge, which primarily serves domestic tourism, the Hong Kong-Zhuhai-Macao Bridge has a global economic impact, reinforcing China's status as a world-class commercial hub. The Huajang Gorge Bridge, under construction in Guizhou Province, is set to become the world's tallest bridge upon its completion in June 2025, soaring at an astounding 250 feet, 3 times higher than the Walt Whitman Bridge in Philadelphia, USA, which stands at 683 feet. Spanning 1.8 miles, this steel girder suspension bridge crosses the Huajang River, where deep gorges and fierce winds pose formidable engineering challenges. With a cost of $283 million, this project exemplifies the extraordinary ability of Chinese engineers to tame treacherous terrain, surpassing U.S. high-altitude bridge projects in both scale and complexity. The bridge employs 120 pairs of suspension cables, each over 3,000 feet long, crafted from high-strength alloy steel with a tensile strength of 2,000 PA, triple the international standard. A standout innovation is the helicopter-assisted cable installation technique, where specialized helicopters ferry cables across the gorge, slashing construction time by 40% compared to traditional crane methods. The main steel girder, weighing 10,000 tons, was forged using continuous casting technology, ensuring precision within 0.3 inches. To anchor the foundation piers over 100 feet deep into rocky cliffs, engineers utilized ultrasonic drilling machines, enabling precise boring in unstable granite terrain, a method never applied in U.S. bridge projects like the Walt Whitman Bridge. The project also leverages 4D wind simulation technology to analyze the impact of 90-mile-per-hour gusts, ensuring stability in extreme weather. Engineers designed the steel girder with an aerodynamic lattice structure, reducing wind resistance and enhancing durability. Compared to the Walt Whitman Bridge, built with 1950s technology and taking 7 years to complete, the Huajang Gorge Bridge is on track for completion in just 5 years, showcasing China's superior speed and efficiency. The Huajang Gorge Bridge will cut travel time across the gorge from 70 minutes to just 1 minute, boosting tourism in Guizhou with an expected 1 million visitors annually, contributing 200 million to the local economy. The project has generated over 15,000 jobs, spanning construction to tourism services. Socially, the bridge enhances healthcare access with a 30% increase in rural patients reaching central hospitals. Unlike the Walt Whitman Bridge, which primarily serves urban transit, the Huajang Gorge Bridge has far-reaching impacts, transforming a remote region into a thriving tourism and economic hub. The Panjang Bridge, also known as the Duge Bridge, holds the title of the world's tallest bridge, soaring at an astonishing 1,854 feet, 3 times higher than the Commodore Barry Bridge in Pennsylvania, USA, which stands at 606 feet. Located at the border of Guizhou and Yunnan provinces, this cable-stayed bridge spans 0.83 miles across the Beipan River, where a deep gorge and 45-degree slopes present unprecedented engineering challenges. Completed in 2016 at a cost of $147 million, this structure is a testament to the unparalleled ability of Chinese engineers to conquer record-breaking heights, far surpassing U.S. bridge projects in both altitude and construction speed. The project utilized 30,000 tons of steel and 112 pairs of cables, each over 2,000 feet long, with a tensile strength of 1,800 MPa. A standout innovation is the automated cable installation technology, where precision-programmed robots handled cable deployment, cutting construction time by 30%. Engineers also employed 3D tensile force simulation to optimize load distribution across the cables, ensuring the bridge can withstand heavy vehicle loads and winds of up to 80 miles per hour. Foundation piers sunk over 80 feet deep were drilled using high-powered pneumatic drilling machines, securing stability in the region's unstable limestone terrain. Compared to the Commodore Barry Bridge, which took over 6 years to build, the Panjang Bridge was completed in just 3 years, demonstrating remarkable efficiency. Engineers used plasma welding technology to join 120-foot steel girder segments, ensuring welds capable of withstanding 3 times the standard pressure. A polymer-based anti-corrosion coating was applied to the cables, extending the bridge's lifespan beyond 100 years. The Panjang Bridge has slashed travel time between Guizhou and Yunnan from 5 hours to just 1, boosting agricultural and mineral cargo traffic by 25%, and contributing $150 million annually to the regional economy. The project created over 12,000 jobs and has spurred tourism, attracting more than 200,000 visitors yearly to admire the stunning gorge views. Socially, the bridge has enhanced educational access, with a 20% increase in high school enrollment in the area. Unlike the Commodore Barry Bridge, which primarily serves industrial traffic, the Panjang Bridge has profound economic and social impacts, transforming a rugged region into a hub of development and showcasing the extraordinary capabilities of Chinese engineers. Located in the Pearl River Delta of Guangdong Province, the Shizyang Bridge is being constructed to claim the title of the world's longest main-span suspension bridge, boasting a central span of 752 feet, over 1.5 miles, surpassing the current record held by Turkey's Çanakkale Bridge, 637 feet. Compared to the Golden Gate Bridge in the U.S. with its main span of just 200 feet, The Shizyang Bridge is nearly twice as long, embodying the extraordinary ambition and technical prowess of Chinese engineers. Upon completion, this bridge will not only serve as a vital transportation link, but also stand as a beacon of innovation, reinforcing the Guangdong Hong Kong-Macau Greater Bay Area's status as a global economic powerhouse. The Shizyang Bridge is a double-deck suspension bridge accommodating both road and rail traffic, with main towers soaring over 1,148 feet, equivalent to a 100-story skyscraper. To achieve its record-breaking main span, Chinese engineers designed suspension cables with a tensile strength of 2D500 MPa, using advanced alloy steel capable of withstanding 3 times the international standard load. A unique feature of the project is its center pier-free design, requiring absolute precision to ensure stability under typhoon winds and heavy traffic loads. Engineers employed 3D aerodynamic simulation technology, testing over 10,000 weather scenarios in wind tunnel labs to optimize the bridge's shape, minimizing vibrations and winds up to 100 miles per hour. The project consumes over 200,000 tons of steel and 1.5 million cubic yards of concrete, with an estimated cost of $2 billion. A groundbreaking innovation of the Shizyang Bridge is its reverse casting method for tower construction. Instead of building towers from the ground up, engineers prefabricated 50-foot tower segments in factories, then used specialized hydraulic cranes to assemble them from the top down, reducing construction time by 25% and enhancing safety. Advanced laser measurement technology ensured tower alignment with an error margin of just 0.04 inches, an extraordinary feat at this scale. Additionally, engineers developed smart suspension cables with a specialized anti-corrosion coating, extending the bridge's lifespan beyond 120 years, far surpassing the 80-year average lifespan of U.S. suspension bridges like the Verrazano Narrows. The Shizyang Bridge is a cornerstone of the Greater Bay Area's development strategy, connecting major cities like Shenzhen and Guangzhou, cutting travel time from 2 hours to just 30 minutes. This is expected to boost cargo and passenger traffic by 15%, contributing billions of dollars annually to the regional GDP. The bridge has created over 50,000 jobs during construction and will support the growth of high-tech industries, positioning the Greater Bay Area to rival Silicon Valley. Socially, it fosters cultural exchange between cities, drawing millions of tourists annually, with its unique double-deck design and stunning views of the Pearl River Delta. Compared to U.S. projects like the San Francisco-Oakland Bay Bridge, which primarily serves local traffic, the Shizyang Bridge has a global economic impact, showcasing the remarkable ability of Chinese engineers to create transformative infrastructure that reshapes entire regions. Nestled among the sheer cliffs of Hubei province, the Sidu River Bridge is an engineering masterpiece, holding the title of one of the world's tallest suspension bridges at a staggering 1,627 feet, nearly twice the height of the New River Gorge Bridge in the U.S. 876 feet. Completed in 2009, this bridge spans the Sidu River, where a deep gorge and fierce winds pose seemingly insurmountable technical challenges. With a length of 0.85 miles and a main span of 953 feet, the Sidu River Bridge not only enhances connectivity in mountainous terrain, but also stands as a symbol of Chinese ingenuity and engineering brilliance, surpassing U.S. suspension bridge projects in both height and complexity. The project utilized over 20,000 tons of steel and suspension cables, stretching more than 3,937 feet each, crafted from specialized alloy steel, with a tensile strength of 1,900 MPa, double the international standard. At a construction cost of approximately $100 million, the project is remarkably cost-efficient for its scale thanks to optimized construction techniques. The most striking innovation of the Sidu River Bridge is its pioneering rocket-assisted cable launching method, a world first. Engineers employed a small rocket to shoot a pilot cable across the 600-foot deep gorge, then used it to pull the heavy main cables across a 0.75-mile gap. This technique saved 30% of construction time and reduced risks for workers in high winds and dense fog. To ensure stability, Chinese engineers designed foundation piers sunk over 65 feet into the cliffs, drilled using high-powered hydraulic machines operated remotely to minimize danger. Another unique feature is the aerodynamic box girder system, designed with a specialized geometric shape to reduce wind resistance, enabling the bridge to withstand 80-mile-per-hour gusts without vibration. The 100-foot girder segments were prefabricated in factories and transported via specialized trucks through rugged mountain terrain, a logistical feat unmatched by U.S. bridge projects like the New River Gorge Bridge at this scale. A mechanical monitoring system equipped with pressure and tension sensors was integrated to track cable conditions, ensuring a bridge lifespan of up to 100 years. The Sidu River Bridge has transformed transportation in Hubei province, connecting once isolated mountain communities and slashing travel time from 3 hours to just 20 minutes. This has boosted the local economy, with agricultural production and tourism value rising by 25% within 5 years of completion. The bridge has become a renowned tourist attraction, drawing thousands annually for its breathtaking gorge views and thrilling pedestrian walkway. The project created over 10,000 direct and indirect jobs, paving the way for small-scale industries like handicraft production and tourism services in the region. Compared to high-altitude U.S. bridges like the Royal Gorge, which primarily serve tourism with limited economic impact, the Sidu River Bridge has far-reaching effects, transforming a remote mountainous area into a hub of development. This structure stands as a testament to Chinese engineers' ability to conquer harsh terrain, delivering sustainable economic and social benefits, while setting a new global benchmark for bridge construction. Nestled amidst the majestic mountains of Yunnan province, the Pulley Bridge ranks among the world's tallest suspension bridges, towering at 1,591 feet. Spanning the valley connecting Baoshan and Pulley towns, this bridge is not only an engineering triumph, but also a premier tourist attraction, drawing thousands of visitors annually with its breathtaking views of the mountainous landscape. Stretching 0.65 miles, the Pulley Bridge showcases the remarkable ability of Chinese engineers to blend cutting-edge technology with tourism development, a feat where U.S. bridge projects like the New River Gorge Bridge fall short. The project utilized over 15,000 tons of lightweight alloy steel, specially designed to reduce weight while maintaining strength, with suspension cables extending over 500 feet each, boasting a tensile strength of 150 MPa. A standout innovation is the unique aerial assembly method, where engineers use temporary suspension cables to transport and install 80-foot steel girder segments directly at the site, eliminating the need to haul materials from the valley below. This approach slashed construction time by 35% and removed the need for temporary access roads, saving millions of dollars. To ensure precision, Chinese engineers deployed 3D laser scanning technology, aligning cables with an error margin of just 0.06 inches, a remarkable achievement amidst dense fog and strong mountain winds. The Pulley Bridge is designed with a distinctive aerodynamic shape, incorporating triangular steel girders to minimize wind resistance, ensuring stability in gusts up to 75 miles per hour. Engineers applied advanced anti-corrosion coating technology to the cables using heat-resistant polymer compounds to maintain durability in Yunnan's humid environment, with a projected lifespan of 100 years. Unlike U.S. suspension bridges like the Mackinac Bridge, which are not optimized for tourism, the Pulley Bridge features integrated pedestrian walkways and scenic viewpoints, offering visitors a unique experience. Completed in 3 years at a cost of approximately $80 million, the project demonstrates superior efficiency compared to U.S. bridge projects, which often take over a decade. The Pulley Bridge has transformed the economic landscape of Wanwei, Yunnan, by connecting isolated mountain communities, reducing travel time from 2 hours to just 15 minutes. This has boosted local commerce, with exports of agricultural products like tea and herbs rising by 30% in the first year after completion. Tourism has flourished, with over 500,000 visitors annually drawn to the bridge's stunning mountain views, and activities like hiking and photography, contributing more than $50 million to the local economy. The project created over 8,000 direct and indirect jobs, fostering the growth of small businesses such as restaurants and hotels. Socially, the bridge has improved access to education and healthcare for remote communities, with a 20% increase in school attendance due to enhanced transportation. Compared to U.S. tourism-focused bridges, the Pulley Bridge is not just a scenic landmark, but a catalyst for sustainable economic and social development, setting a new standard for integrating infrastructure with regional growth. Spanning the mighty Yangze River, the Changtai, Yangtze River Bridge holds the title of the world's longest main-span cable-stayed bridge, with a central span stretching an impressive 3,963 feet, surpassing Russia's Russky Bridge, 622 feet. Completed in 2024, this bridge connects the cities of Changzhou and Taizhou in Jiangsu province, with a total length exceeding 6.2 miles. Compared to the Taguima Narrow Bridge in the U.S. with a main span of just 2,800 feet, the Changtai Bridge represents a monumental leap forward, showcasing the superior engineering expertise of Chinese engineers. Built at a cost of approximately $1.5 billion, this structure is not only a technical triumph but also a catalyst for economic growth in the Yangtze River Delta, one of China's most dynamic economic regions. The Changtai Bridge is designed to accommodate both road and rail traffic, featuring an upper deck with 6 vehicle lanes and a lower deck with 4 railway tracks. The project utilized over 250,000 tons of steel and 2 million cubic yards of concrete, including the world's longest continuous steel girder, 963 feet, crafted from high-strength steel with a tensile strength of 1,800 MPa. A standout innovation is the advanced push-out casting technique, where steel girder segments were cast on-site and extended from both ends of the bridge using high-capacity hydraulic systems, ensuring precision and reducing construction time by 20% compared to traditional methods. The bridge's main towers, rising over 820 feet, are constructed from high-strength reinforced concrete, with foundation piers sunk more than 100 feet below the riverbed to withstand the Yangtze's strong currents and sediment. To ensure stability, Chinese engineers employed advanced vibration analysis technology using mathematical models to predict the impact of traffic loads and typhoon winds up to 90 miles per hour. They also implemented ultra-durable cable systems coated with a nano-based anti-corrosion compound, extending cable lifespan beyond 100 years, surpassing the 70-year lifespan of cables on U.S. cable-stayed bridges like the Delaware Memorial Bridge. High-powered laser welding technology was used to join steel girder segments, ensuring welds capable of withstanding 3 times the international standard pressure. Unlike U.S. cable-stayed bridge projects, which often take over a decade, the Changtai Bridge was completed in just 5 years, highlighting China's remarkable efficiency and speed. The Changtai Yangtze River Bridge has transformed transportation in Jiangsu province, slashing travel time between Changzhou and Taizhou from 90 minutes to just 20 minutes, boosting cargo and passenger traffic by 40%. This has propelled the Yangtze River Delta, which accounts for 20% of China's GDP, to achieve an additional $2 billion in annual economic growth through improved logistics and commerce. The project created over 30,000 jobs during construction and supports the growth of industries such as automotive manufacturing and electronics in both cities. Socially, the bridge has enhanced access to healthcare and education, with a 25% increase in patients from Taizhou accessing major hospitals in Changzhou. The bridge also serves as an icon of modern development, attracting tourists and investors and reinforcing Jiangsu's position as an economic hub. Compared to U.S. and cable-stayed bridges like the Sunshine Skyway, which primarily impact local economies, the Changtai Bridge has national and international significance, underscoring the ability of Chinese engineers to create transformative infrastructure that reshapes economic and social landscapes. Nestled among the majestic mountain ranges of Guizhou province, the Baling Bridge is an engineering marvel that spans the Baling River Valley at an elevation of 1,214 feet, more than 3 times the height of Michigan's Mackinac Bridge, 552 feet. Completed in 2009 at a cost of $210 million, this 1.39-mile-long cable-stayed bridge boasts a main span of 3,570 feet and serves as a key highway link between Anshun and Guiyang. With its cables arching across the gorge like gigantic threads, the Baling Bridge is not just a transportation structure, but also the highest bungee jumping point in the world, recognized by Guinness in 2019, attracting thousands of adventurous tourists each year. The project utilized 25,000 tons of steel and 400,000 cubic yards of concrete, with 2 main towers rising 614 feet, equivalent to a 50-story building. The standout technical feature is the hydraulic cable pulling technology, where high-strength alloy steel cables with a tensile strength of 2,100 MPa were pulled across the deep gorge using a temporary cable car system, achieving an accuracy of under 0.15 inches. This technique reduced construction time by 25% compared to traditional cable pulling methods, saving millions of dollars. Engineers used 3D aerodynamics simulations and analyzed over 6,000 weather scenarios to ensure the bridge could withstand 75 km/h winds and a 7.0 magnitude earthquake. The 80-foot deep foundation piles were drilled into limestone using high-powered drilling machines, ensuring stability in the complex terrain of Guizhou. To build in such a treacherous gorge, engineers employed a 200-foot cable car system to transport materials, enabling the movement of heavy steel sections to positions inaccessible by road. The corrosion-resistant polymer coating on the cables extends the bridge's lifespan to over 100 years, far surpassing the 60-year lifespan of the Mackinac Bridge. Compared to the Mackinac Bridge, which took 7 years to complete, the Baling Bridge was finished in just 4 years, showcasing China's remarkable efficiency. The Baling Bridge has reduced travel time between Anshan and Guiyang from 2.5 hours to just 30 minutes, boosting freight traffic by 20%, especially agricultural products and minerals contributing 50 million annually to the economy of Guizhou. The project has created over 10,000 jobs, ranging from construction to adventure tourism, and attracts more than 200,000 tourists annually due to its unique bungee experience. Socially, the bridge has improved access to healthcare, with a 15% increase in patients traveling from rural areas to Guiyang's hospitals. It has also boosted trade with exports from Anshan, rising by 12%. While the Mackinac Bridge mainly serves inter-island traffic, the Baling Bridge has transformed the mountainous region into an economic and tourism hub. Located in Guizhou Province, the Chinguhi Bridge stands as one of the highest suspension bridges in the world, spanning the Chinguhi River at a height of 1,332 feet, more than 4 times the height of Florida's Sunshine Skyway Bridge, 310 feet. Completed in 2016 at a cost of $180 million, this 1.35-mile-long bridge has a main span of 3,710 feet and connects the Guizhou and Yangze expressways. With its steel cables stretching across the gorge like giant birdwings, the Chinguhi Bridge is not just an engineering marvel, but also a symbol of connection, unlocking economic opportunities for the mountain communities. The project utilized 28,000 tons of steel and 350,000 cubic yards of concrete, with 2 main towers standing 755 feet tall. The standout technical feature is the synchronized steel beam assembly technology, where 130-foot-long steel beams were lifted simultaneously from both sides of the gorge using 800-ton cranes, reducing construction time by 20%. Engineers employed 3D tension simulations and analyzed over 5,000 scenarios to ensure the bridge could withstand 80 km/h winds and a 7.5 magnitude earthquake. The 70-foot deep foundation piles were cast with crack-resistant concrete and used high-pressure pumping technology to counteract the unstable limestone geology. The nano-coated corrosion protection extends the bridge's lifespan to over 100 years, far surpassing the Sunshine Skyway Bridge's 50-year lifespan. To work in the treacherous terrain, engineers implemented a 1,500-foot cable car system to transport materials across the gorge without the need for a temporary road. Compared to the Sunshine Skyway, which took 6 years to complete, the Chinguhi Bridge was finished in just 4 years, showcasing China's superior speed. The bridge has reduced travel time from Guiyang to Yangze from 3 hours to just 40 minutes, boosting freight traffic by 25% and contributing $60 million annually to the regional economy. The project has created over 12,000 jobs, ranging from construction to tourism, and attracts more than 250,000 visitors every year due to its stunning landscape. Socially, the bridge has improved access to education with an 18% increase in students traveling from rural areas to secondary schools. It has also boosted agricultural exports by 15%. Unlike the Sunshine Skyway, which primarily serves urban traffic, the Chinguhi Bridge has transformed the Guizhou mountain region into a new economic hub. Completed in June 2024, the Shenzhen-Zhongshan Link is the world's longest sea-crossing bridge tunnel system, stretching an impressive 15 miles across the Pearl River estuary in Guangdong province connecting Shenzhen and Zhongshan. With a cost of $4.83 billion, this monumental project slashes travel time from 2 hours to just 20 minutes, positioning the Greater Bay Area as a global economic powerhouse rivaling Silicon Valley. Compared to New York's Throgs Neck Bridge, which spans a mere 2.9 miles, the Shenzhen-Zhongshan Link is over 5 times longer and far more complex, breaking 10 world records, including the longest steel span, 466 feet, and the longest immersed tunnel, 4.2 miles. The project utilized 290,000 tons of steel and 2.6 million cubic yards of self-compacting concrete, featuring 2 artificial islands and a submerged tunnel 30 feet below the sea. A standout technical achievement is the advanced immersed tunnel casting technology, where 540-foot-long, 80,000-ton tunnel segments were prefabricated onshore and sunk into place using hydraulic cable systems, achieving precision within 0.2 inches. Engineers employed 4D flow simulation to design the structure to withstand Category 16 typhoons winds of 125 miles per hour and 20-foot waves. The 230-foot-long steel box girders were assembled using plasma welding robots, cutting construction time by 25% compared to manual methods. A polymer-based anti-corrosion coating was applied to the steel cables, extending the bridge's lifespan beyond 120 years, far surpassing the 70-year lifespan of the Throgs Neck Bridge. To construct in the harsh marine environment, engineers implemented prefabricated artificial island technology, deploying 6,000-ton concrete blocks installed within 6 months using high-capacity floating cranes. The bridge features color-changing LED lighting powered by solar energy, saving 30% in energy consumption, while providing intuitive traffic signals, a feature absent in U.S. bridges like the Throgs Neck. While the Throgs Neck Bridge took 8 years to complete, the Shenzhen-Zhongshan Link was finished in 7 years, showcasing China's superior efficiency. The link has boosted cargo traffic between Shenzhen and Zhongshan by 25%, contributing $2 billion annually to the regional economy and creating over 30,000 jobs in construction, logistics, and tourism. Socially, it has spurred tourism with over 1 million visitors annually, while improving healthcare access with a 20% increase in patients reaching regional hospitals. The bridge also fosters cultural exchange with a 15% rise in trade and arts events between the two cities. Unlike the Throgs Neck Bridge, which primarily serves local urban traffic, the Shenzhen-Zhongshan Link has a global economic impact, solidifying China's position as a world-class commercial hub. Nestled amidst the majestic mountains of Hunan province, the Azai Bridge is an engineering marvel that spans the Danyong River Valley at a height of 165 feet, more than 7 times the height of the Lake Pontchartrain Causeway in Louisiana, and a USA 160 feet. Completed in 2012 at a cost of $200 million, this 0.73-mile-long suspension bridge has a main span of 858 feet and is part of the G65 expressway connecting Chongqing and Changsha. With its steel cables stretching across the gorge like a giant silk ribbon, the Azai Bridge is not only a transportation structure, but also a tourism symbol, attracting millions of visitors to witness the breathtaking landscape of the Western Miao and Dong ethnic region. The project utilized 22,000 tons of steel and 320,000 cubic yards of concrete, with 2 main towers rising 492 feet, equivalent to a 40-story building. The standout technical feature is the aerial cable pulling technology, where high-strength alloy steel cables with a tensile strength of 2,000 MPa were pulled across the 165-foot deep gorge using a temporary cable car system, achieving an accuracy of under 0.1 inches. This method reduced construction time by 30% compared to traditional techniques, saving millions of dollars. Engineers used 3D aerodynamics simulations and analyzed over 7,000 weather scenarios to ensure the bridge could withstand 70 mph winds and a 7.0 magnitude earthquake. The 65-foot deep foundation piles were drilled into granite using high-powered drills, ensuring stability in the rugged terrain. To build in such a deep gorge, engineers deployed a 1,000-foot cable car system to transport heavy steel sections to positions inaccessible by road. A corrosion-resistant polymer coating protects the cables, extending the bridge's lifespan to over 100 years, far exceeding the 50-year lifespan of the Lake Pontchartrain Causeway. Compared to the 8-year construction time of the Lake Pontchartrain Causeway, the Azai Bridge was completed in just 4 years, demonstrating China's superior speed and infrastructure development. The Azai Bridge has reduced travel time through the Danyong Valley from 2 hours to just 5 minutes, boosting freight traffic by 25%, especially agricultural products and handicrafts from the Miao and Dong ethnic groups. The bridge contributes $45 million annually to Hunan's economy and attracts more than 1.5 million visitors thanks to its gorge views and ethnic festivals. The project has created over 9,000 jobs, ranging from construction to tourism services, and has improved access to education with an 18% increase in students traveling from the Western Macau region to secondary schools. Unlike the Lake Pontchartrain Causeway, which mainly serves urban traffic, the Azai Bridge has transformed the ethnic minority region into a tourism and economic hub, showcasing China's ingenuity and infrastructure development. Located in Wuhan, Hubei Province, the Yangtze River Bridge holds the record as the world's longest double-deck suspension bridge with a main span stretching an impressive 5,477 feet. Completed in 2019 at a cost of $1.2 billion, this 2.6-mile bridge spans the Yangtze River, accommodating 8 vehicle lanes on the upper deck and a metro line on the lower deck, seamlessly connecting both sides of Wuhan. Compared to New York's Triborough Bridge with a main span of just 1,380 feet, the Shizyang Bridge surpasses it fourfold in span length and multifunctional design, showcasing China's advanced engineering prowess. The project utilized 100,000 tons of steel and 1.5 million cubic yards of concrete, featuring 2 towers soaring 820 feet. A standout technical achievement is the double-deck steel girder technology, with 180-foot steel girders designed to handle twice the load of standard suspension bridges, ensuring safety for both vehicular and metro traffic. Engineers employed helicopter-assisted cable installation, positioning 3,000-foot steel cables at a height of 650 feet with precision within 0.15 inches. The foundation piers, sunk 90 feet deep, were cast with corrosion-resistant concrete using high-pressure pumping technology to ensure durability in the river's humid environment. The bridge was designed with 3D wind simulation, analyzing over 8,000 scenarios to withstand winds of 80 miles per hour and earthquakes up to 7 on the Richter scale. To boost construction efficiency, engineers implemented synchronized steel girder assembly, lifting and installing girder segments simultaneously from both riverbanks, reducing construction time by 20% compared to traditional methods. A polymer-based anti-corrosion coating was applied to the steel cables, extending the bridge's lifespan beyond 100 years, far surpassing the 60-year lifespan of the Triborough Bridge. While the Triborough Bridge took 6 years to complete, the Shizyang Bridge was finished in just 4 years, demonstrating China's superior efficiency. The Shizyang Bridge has slashed travel time across the Yangtze River from 40 minutes to just 5 minutes, boosting traffic flow by 20% and contributing $800 million annually to Wuhan's economy. The project created over 15,000 jobs spanning construction to metro operations and has driven tourism, attracting over 500,000 visitors yearly to admire its unique double-deck design. Socially, the bridge has enhanced urban mobility, with metro ridership increasing by 25% and improved healthcare access, with a 15% rise in patients reaching regional hospitals. Unlike the Triborough Bridge, which primarily serves local traffic, the Shizyang Bridge has a broader impact, integrating road and rail to solidify Wuhan's status as a leading urban hub. The Kaohsiunmin Bridge, located in Chongqing, is the longest steel arch bridge in the world, with a main span of 1,811 feet. Completed in 2009 at a cost of $500 million, this 1.1-mile-long bridge spans the Yangtze River, connecting 3 bustling commercial districts of Chongqing, Jiangbei, Nainan, and Wulong. In comparison to the Robert F. Kennedy Bridge in New York, USA, which has a main span of only 1,380 feet, Kaohsiaman excels in its scale and steel arch design, showcasing the advanced engineering capabilities of Chinese engineers in overcoming the challenging Yangtze River. The project used more than 50,000 tons of steel and 600,000 cubic yards of concrete, with the steel arch towering 465 feet, equivalent to a 40-story building. A key technical feature is the modular steel arch assembly technology, in which arch segments weighing 1,000 tons are precast at a factory and lifted into place by large cranes, achieving an accuracy of less than 0.15 inches. This technique reduced construction time by 20% compared to traditional arch construction methods, saving tens of millions of dollars. Engineers used 3D tensile simulations to analyze a 40,000-ton load, ensuring that the steel arch could withstand the pressure from 6 lanes of traffic and winds at speeds of 75 miles per hour. The deep 70-foot foundations were drilled using high-power hydraulic drills, penetrating the complex limestone terrain of the Yangtze River, ensuring stability in the humid environment. To prevent corrosion, the steel arch was coated with an advanced graphene composite, extending the bridge's lifespan to over 100 years, far surpassing the 60-year lifespan of the Robert F. Kennedy Bridge. Engineers also implemented beam casting technology using 100-foot-long steel beams to connect the arch to the bridge deck, enhancing durability and reducing vibrations. In contrast to the Robert F. Kennedy Bridge, which took 6 years to complete using traditional methods, Kaohsiaman was finished in just 4 years, demonstrating China's superior efficiency. The Kaohsiaman Bridge reduced travel time across the Yangtze River from 30 minutes to 4 minutes, increasing freight traffic by 15% and contributing $600 million annually to Chongqing's economy through trade and logistics. The project created over 10,000 jobs, ranging from construction to tourism services, and attracts more than 300,000 visitors each year due to its spectacular steel arch design and views of the river. Socially, the bridge has improved access to healthcare, with the number of patients traveling from Nanyang on to the Zhong Bay Central Hospital increasing by 20%. The bridge has also fostered cultural exchange, with art and trade events in Chongqing rising by 10%. Compared to the Robert F. Kennedy Bridge, which primarily serves urban traffic, Kaohsiaman has a profound economic and social impact, reinforcing Chongqing as a leading commercial hub. The Lupu Bridge, located in Shanghai, is the second longest steel arch bridge in the world, completed in 2003, with a main span of 1,804 feet and a total length of 2.4 miles. Built at a cost of $300 million, this bridge spans the Huangpu River, connecting the Luan district with the financial hub of Pudong, the economic center of China. In comparison to the Walt Whitman Bridge in Philadelphia, USA, with a main span of only 1,150 feet, Lupu Bridge stands out in terms of scale and architectural design, becoming a symbol of Shanghai's modern development. The project used 35,000 tons of steel and 500,000 cubic yards of concrete, with the steel arch soaring to 328 feet. A key technical feature is the curved arch welding technology, where 100-foot steel sections are joined using high-powered plasma welding robots, achieving accuracy within 0.15 inches. This technique tripled the durability of the welds compared to international standards, ensuring the arch can withstand a 30,000-ton load. The deep 80-foot foundations are cast with waterproof concrete using high-pressure pumping technology to counteract the strong current of the Huangpu River. Engineers use 3D aerodynamic simulations, analyzing over 5,000 weather scenarios to ensure the bridge's stability against winds at speeds of 70 miles per hour and earthquakes of 7.0 magnitude on the Richter scale. For construction, engineers employed the full arch lifting technology, where the steel arch was assembled on shore and then lifted into place by 2 800-ton cranes, reducing construction time by 15% compared to traditional methods. A corrosion-resistant epoxy coating was applied to the steel arch, extending its lifespan to over 100 years, far exceeding the 50-year lifespan of the Walt Whitman Bridge. In contrast to the Walt Whitman Bridge, which took 7 years to complete, the Lupu Bridge was finished in 3 years, demonstrating China's remarkable speed and efficiency. The Lupu Bridge reduced travel time from Luan to Pudong from 25 minutes to just 5 minutes, increasing traffic flow by 20% and contributing $400 million annually to Shanghai's economy through trade and financial services. The project created over 8,000 jobs and boosted tourism with more than 200,000 visitors each year coming to admire the curved arch design and views of the Huangpu River. Socially, the bridge improved access to education with the number of students traveling from Luan to universities in Pudong increasing by 15%. It also enhanced cultural exchange with exhibition events in Pudong rising by 10%. Compared to the Walt Whitman Bridge, which mainly serves urban traffic, the Lupu Bridge has a greater economic and social impact, reinforcing Shanghai's position as a global financial center. The Hongjo Bay Bridge, completed in 2008, is the longest sea bridge in China, stretching 22 miles across Hongjo Bay, connecting Ningbo and Shanghai. With a cost of $1.42 billion, this bridge shortens the distance from 250 miles to 175 miles, turning Hongjo Bay into a major transportation hub. Compared to the Tobin Bridge in Boston, USA, which is only 2.3 miles long, the Hongjo Bay Bridge surpasses it in length and complexity by nearly 10 times, showcasing the ability of Chinese engineers to conquer the harsh marine environment. The project used 250,000 tons of steel and 2 million cubic yards of concrete, with 6 lanes of traffic and a design speed of 62 miles per hour. A notable technical feature is the storm-resistant cable technology, utilizing alloy steel cables with a tensile strength of 2,000 MPa, designed to withstand winds at speeds of 100 miles per hour and waves up to 15 feet high. Engineers use box girder casting technology with 230-foot-long girder sections produced at a factory and lifted into place using a 1,000-ton floating crane, achieving an accuracy of less than 0.2 inches. The deep 100-foot foundations were drilled using hydraulic drills with corrosion-resistant concrete to ensure durability in the salty marine environment. The bridge was designed using 3D wave simulations, analyzing over 7,000 weather scenarios to optimize its aerodynamics. To increase construction efficiency, engineers implement continuous girder assembly technology, where girder sections were assembled at sea using a temporary cable pulling system, reducing construction time by 20%. A polymer anti-corrosion coating was applied to the steel cables, extending the bridge's lifespan to over 100 years, far exceeding the 60-year lifespan of the Tobin Bridge. Compared to the Tobin Bridge, which took 6 years to complete, the Hongjo Bay Bridge was finished in 5 years, demonstrating superior efficiency. The Hongjo Bay Bridge reduced travel time from 4 hours to 2.5 hours, increasing freight traffic by 25% and contributing $1.5 billion annually to the regional economy through trade and logistics. The project created over 20,000 jobs, ranging from construction to tourism services, and attracts more than 600,000 visitors each year due to its breathtaking views of Hongjo Bay. Socially, the bridge improved access to healthcare, with the number of patients traveling from Ningbo to Shanghai's hospitals increasing by 20%. The bridge also boosted trade, with exports from Ningbo rising by 15%. Compared to the Tobin Bridge, which primarily serves urban traffic, the Hongjo Bay Bridge has a national economic impact, reinforcing the position of the Yangtze River Delta region. The Xiao Bay Bridge, located in Qingdao, Shandong Province, was once recorded as the longest sea bridge in the world when it was completed in 2011 with a total length of 26.4 miles. With a cost of $2.3 billion, this bridge spans the Xiao Bay, connecting downtown Qingdao with Huangdao Island, cutting travel time from 40 minutes to just 20 minutes. Compared to the Arthur Ravenel Jr. Bridge in South Carolina, USA, which is only 2.7 miles long, the Xiao Bay Bridge exceeds it by nearly 10 times in length, demonstrating China's advanced engineering capabilities in building large-scale sea crossings. The project used over 450,000 tons of steel and 3.5 million cubic yards of concrete, with more than 5,000 bridge piers built on soft soil and salty marine environments. A key technical feature is the modular concrete girder casting technology, where 130-foot-long girder sections are produced at factories with accuracy within 0.2 inches, then transported by barges and assembled using a 1,200-ton floating crane. This technique reduced construction time by 25%, compared to on-site casting methods, saving tens of millions of dollars. Engineers use 3D sea wave simulations analyzing over 7,000 weather scenarios to design the bridge to withstand a Category 14 hurricane winds of 100 miles per hour and earthquakes of 8.0 magnitude on the Richter scale. The 80-foot deep piers are cast with corrosion-resistant concrete, utilizing high-pressure concrete pumping technology to ensure durability in the marine environment. The concrete girders are designed with a double-box structure, doubling the load-bearing capacity compared to typical bridges, ensuring safety for 6 lanes of traffic. In comparison to the Arthur Ravenel Jr. Bridge, which took 7 years to complete, the Hongjo Bay Bridge was finished in 4 years, demonstrating exceptional efficiency. A corrosion-resistant epoxy coating was applied to the steel cables, extending the bridge's lifespan to over 100 years, far surpassing the 60-year lifespan of the Arthur Ravenel Jr. Bridge. The Hongjo Bay Bridge increased traffic and freight volume by 30%, contributing $1.2 billion annually to Qingdao's economy through trade and logistics. The project created over 25,000 jobs from construction to tourism services and attracts over 700,000 visitors annually thanks to its stunning views of Hongjo Bay. Socially, the bridge improved access to education, with the number of students traveling from Huangdao Island to universities in Qingdao increasing by 18%. The bridge also boosted trade, with Qingdao's exports rising by 15%. Compared to the Arthur Ravenel Jr. Bridge, which mainly serves local traffic, the Hongjo Bay Bridge has a national economic impact, strengthening Qingdao's position as a leading seaport hub. The Wanwei Bridge, completed in 2008, is the 5th longest railway bridge in the world, spanning 49.5 miles along the Zhengzhou-Xi'an high-speed rail line in Shanxi province. With a cost of $1.8 billion, this bridge crosses the Wei River twice, connecting key inland cities. Compared to the Walt Whitman Bridge in Philadelphia, USA, which is only 2.2 miles long, the Wanwei Bridge exceeds it by over 20 times in length, showcasing China's capability in building large-scale railway infrastructure. The project used 300,000 tons of steel and 2.8 million cubic yards of concrete, with more than 2,000 bridge piers averaging 100 feet in height. A key technical feature is the precast piers technology, in which concrete piers are produced in factories and assembled using 800-ton mobile cranes, achieving an accuracy of less than 0.2 inches. This technique reduced construction time by 30% compared to on-site casting methods, saving hundreds of millions of dollars. Engineers use 3D seismic simulations analyzing over 6,000 scenarios to design the bridge to withstand earthquakes of 7.0 magnitude and winds at speeds of 70 miles per hour. The 150-foot steel beams were assembled using hydraulic beam pulling technology, ensuring stability for high-speed trains running at speeds of 217 miles per hour. To prevent corrosion in the humid river environment, the bridge piers were coated with an advanced polymer compound, extending the bridge's lifespan to over 100 years, far exceeding the 50-year lifespan of the Walt Whitman Bridge. Compared to the Walt Whitman Bridge, which took 7 years to complete using traditional methods, the Wanwei Bridge was finished in 4 years, demonstrating superior efficiency. Engineers also employed synchronous girder assembly technology, allowing 2 teams to work from both riverbanks, speeding up construction by an additional 15%. The Wanwei Bridge reduced travel time between Zhengzhou and Xi'an from 6 hours to 2 hours, increasing freight traffic by 20% and contributing $1 billion yearly to the regional economy through trade and transportation. The project created over 18,000 jobs, ranging from construction to logistics, services, and attracts over 400,000 visitors each year to admire the scenic views of the Wei River. Socially, the bridge improved access to healthcare, with the number of patients traveling from rural areas to hospitals in Xi'an increasing by 15%. The bridge also boosted cultural exchange, with trade events rising by 10%. Compared to the Walt Whitman Bridge, which primarily serves urban traffic, the Wanwei Bridge has a profound economic and social impact, strengthening China's high-speed rail network. The Chinguhi Bridge, located in Hunan province, is an impressive suspension bridge that spans the Qixi Valley at a height of 610 feet, completed in 2012. Measuring 1.4 miles in length and costing $200 million, this bridge connects southern China to the eastern coastline, reducing travel time from 1 hour to just 5 minutes. Compared to the Ben Franklin Bridge in Pennsylvania, USA, which has a height of only 135 feet, the Qixi Bridge surpasses it in both height and engineering, showcasing the capabilities of Chinese engineers in overcoming challenging mountainous terrain. The project used 25,000 tons of steel and 400,000 cubic yards of concrete, with 2 towers standing at 492 feet tall. A key technical feature is the rocket cable pulling technology, in which a small rocket is used to carry the lead wire across the 610-foot deep gorge, followed by the pulling of the 2,000-foot-long main steel cables, with a tensile strength of 1,900 MPa. This technique reduced construction time by 25% compared to traditional cable pulling methods, ensuring safety under strong wind conditions. Engineers employed 3D aerodynamic simulations, analyzing over 4,000 weather scenarios, to design the bridge to withstand winds at speeds of 75 miles per hour. The 60-foot deep foundations were drilled using high-power pneumatic drills penetrating granite terrain to ensure stability. The 120-foot steel beams were assembled using synchronous girder lifting technology, where 2 600-ton cranes worked simultaneously from both sides of the valley, reducing construction time by 15%. A corrosion-resistant nano-coating was applied to the steel cables, extending the bridge's lifespan to over 100 years, far surpassing the 60-year lifespan of the Ben Franklin Bridge. Compared to the Ben Franklin Bridge, which took 6 years to complete, the Qixi Bridge was finished in 3 years, demonstrating superior efficiency. The Qixi Bridge increased freight traffic by 15%, particularly for agricultural products and minerals, contributing $300 million annually to the Hunan economy. The project created over 10,000 jobs, ranging from construction to tourism services, and attracts more than 200,000 visitors each year, thanks to its stunning views of the Qixi Valley. Socially, the bridge improved access to education, with the number of students traveling from rural areas to secondary schools increasing by 20%. The bridge also boosted trade, with exports from Hunan rising by 12%. Compared to the Ben Franklin Bridge, which primarily serves urban traffic, the Qixi Bridge has a broader impact, transforming a rural area into an economic and tourism hub. The Shizyang Bridge, located in the Zhoushan Archipelago, Zhejiang Province, is one of the longest suspension bridges over the sea in China, with a main span of 413 feet. It once held the world record when it was completed in 2007. The bridge, with a total length of 1.6 miles and a cost of $360 million, connects Xintang and Sezi Islands, reducing travel time from 1 hour to just 5 minutes. Compared to the Bronx Whitestone Bridge in New York, USA, with a main span of only 300 feet, the Shizyang Bridge excels with a main span more than double its length, demonstrating China's superior engineering in building sea bridges in extreme storm conditions. The project used 38,000 tons of steel and 450,000 cubic yards of concrete, with 2 main towers reaching 692 feet, equivalent to a 60-story building. A key technical feature is the vibration-resistant cable technology, which uses alloy steel cables with a tensile strength of 200 MPa, designed to withstand winds at speeds of 112 miles per hour, a common condition in Zhoushan Bay. Engineers deployed high-power laser welding technology to join 120-foot steel beam sections, achieving an accuracy of less than 0.12 inches, ensuring the durability of the 6-lane bridge. The 90-foot deep piers were cast with corrosion-resistant concrete and use high-pressure pumping technology to counteract strong currents in the salty marine environment. The bridge was designed using 3D aerodynamic simulations, analyzing over 6,000 weather scenarios to reduce vibration and withstand earthquakes of 7.5 magnitude on the Richter scale. For construction in the marine environment, engineers used the floating steel girder assembly technology, where the beams were assembled on barges and lifted into position using 800-ton floating cranes, reducing construction time by 20% compared to traditional methods. A nano-coating anti-corrosion compound was applied to the steel cables, extending the bridge's lifespan to over 100 years, far surpassing the 70-year lifespan of the Bronx Whitestone Bridge. Compared to the Bronx Whitestone Bridge, which took 7 years to complete, the Shizyang Bridge was finished in 4 years, demonstrating China's remarkable efficiency. The Shizyang Bridge increased freight traffic by 20%, particularly seafood and industrial goods between the Zhoushan Islands and the mainland, contributing $500 million annually to Zhejiang's economy. The project created over 12,000 jobs from construction to tourism services and attracts more than 300,000 visitors each year due to its stunning views of the East China Sea. Socially, the bridge improved access to healthcare, with the number of patients traveling from the islands to Ningbo hospitals increasing by 18%. The bridge also boosted trade, with exports from Zhoushan rising by 15%. Compared to the Bronx Whitestone Bridge, which primarily serves urban traffic, the Shizyang Bridge has a more far-reaching impact, transforming the Zhoushan archipelago into a new economic and tourism hub. "20 bridges on this list, from the Danyong Kunshan Grand Bridge stretching over 100 miles to the Huajang Mountain Gorge Bridge soaring over 2,000 feet, are not just feats of transportation engineering, but also shining symbols of China's global leadership in infrastructure. With 12 world records for length, height, and main span, China far surpasses the United States, where 30% of bridges are in urgent need of repair, according to the American Society of Civil Engineers, ASCE. While major bridge projects in the U.S., such as the Ambassador Bridge in Michigan, take over 8 years to complete, China has finished mega projects like the Shenzhen-Zhongshan Link in just 7 years, demonstrating unprecedented speed and efficiency. Each bridge carries its own unique engineering hallmark, from the modular assembly of the Danyong Kunshan Bridge to the rocket cable pulling techniques used in the Sidu River Bridge and Chinguhi Bridge, to the submerged tunnel of the Shenzhen-Zhongshan Link and the ancient stone arch of the Yangze Bridge. Advanced materials like 2500 MPa alloy steel, Category 16 hurricane-resistant concrete carbon fiber, and graphene coatings have greatly extended the lifespan and durability of these bridges, surpassing U.S. standards, where bridges like the Ambassador Bridge still rely on 20th century technology. Innovative construction methods such as incline casting, push casting, laser welding, and 4D aerodynamic simulations have enabled China to cut costs and construction time by 20 to 35%, setting a new global benchmark in the construction industry. The impact of these bridges goes far beyond infrastructure. They have contributed tens of billions of dollars to the economy through trade, tourism, and jobs, while also improving the lives of millions in remote areas. The Pulley River and Chinguhi bridges have turned mountainous regions into tourism hotspots, attracting millions of visitors each year. The Shizyang Shangjingao and Shenzhen Zhongshan links have bolstered economic hubs competing with Silicon Valley, while the Yangze Bridge has preserved historical value, becoming a UNESCO World Heritage Site. Over 200,000 jobs have been created through these projects, ranging from construction to logistics, and millions of people have benefited from improved transportation, healthcare, and education. Looking ahead, China is pioneering with smart bridges integrated with renewable energy, such as the LED lighting system of the Shenzhen-Zhongshan Link, and advanced monitoring technologies promising to reshape the global construction industry. Compared to the U.S., where infrastructure projects are often delayed due to high costs and complex processes, China has proven its ability to turn bold ideas into reality with unprecedented speed and scale. These bridges are not only engineering marvels, but also powerful statements of a nation's ambition to lead the world in infrastructure development. What are your thoughts? Are you impressed with China's top 20 largest bridge projects? Do you think that in the future, the U.S. and other superpowers could create larger projects that surpass these top 20 bridges of China? Share your thoughts in the comments below. Don't forget to subscribe so you won't miss the latest analyses on technology, national strategies, and innovations shaping the future. Top 10 Discoveries. Official will be back with untold stories, boundary-pushing structures, and quiet revolutions that have a global ripple effect. See you in the next video.